I'm going to talk to you a little bit about bioenergy and climate change mitigation scenarios in integrated assessment models. So before jumping into this, I want to give a very quick overview for those who are not fully familiar with integrated assessment models of what is their purpose and how are they used. That will help contextualize some of the results later. So basically, IAMs, as they're known, they aim to assess the interaction between human and natural systems. So how do they do this? They do this by first having certain key inputs, which are assumptions on economic growth or how population may change. These are exogenously put in. And then as well, some other normative assumptions about how some broader aspects may develop. This may be technology development, lifestyle and behavioral choices and things like that. So really normative narrative aspects of how our societies may develop over the next decades. So these inputs are then used to assess the interactions between human and natural systems, which they typically, on the human system, they cover the energy system, so how we supply and demand energy, but also how we supply and demand land through the agricultural system. And then on these connect to the natural system by looking at a representation of nutrient flows, crop growth, and things like that, and also climate representation. And then there's a number of variables that are used to interact between these systems. So for instance, energy and land typically interact a lot through biomass supply and demand. Emissions play a very big role in the interaction between the human and the natural system, but also obviously demand for agricultural products, demand for resources. And then climate change may itself affect the energy system or the agricultural system. So we try to model as much as possible these feedback loops. And then finally, a number of impacts and outcomes are given for the different scenarios. So these models, first of all, are not used to predict the future. They make certain projections and they answer what if type scenarios. So what if we were to have massive behavioral and lifestyle changes? How does that change the possibilities of meeting strict environmental goals? What if certain technologies are or are not available? What are the implications there? They also allow us to investigate the drivers and constraints of change, but also look at different uncertainties and sensitivities. And this is where the methodology of scenario analysis becomes very important. The models are typically used to run many different scenarios, and by contrasting and comparing them, we can get better insight into the sensitivities, uncertainties, and levers of change. So moving on into what do these models say about bioenergy in mitigation scenarios, here are some results from an IPCC special report focusing on 1.5 degree scenarios and 2 degree scenarios concerning bioenergy use. So here we see the primary bioenergy demand for scenarios that either meet the 1.5 target in green or that meet the 2 degree target in purple. And the first thing that we see by comparing the purple and the green lines is that when you try to meet the 1.5 degree target, you're using more bioenergy and you're using it earlier on. So essentially, this shows us that bioenergy plays an active role in climate mitigation. As you increasingly try to meet harder and harder targets, bioenergy is used more. It plays a very, very active role. And there's broad agreement on that. This is basically the same graph, but now only showing the primary bioenergy, which is actually used together with carbon capture and storage. And here is the same graph, but basically showing it as a fraction of the total primary bioenergy demand. So what we see in these two new panels is that a huge amount of this primary bioenergy actually is combined with carbon capture and storage, typically between 50% and 100%. So this shows the importance of BECCS. And BECCS is very important in these mitigation scenarios because in principle, if the bioenergy is grown in a sustainable manner, which is what the IAMs typically assume, then you can get so-called carbon dioxide removal. Because you have the biomass growing, that takes up carbon dioxide during photosynthesis. Then when you convert it and use the fuel, you can capture some or all of the carbon and store it permanently, which leads to a net movement of carbon from the atmosphere to permanent sequestration. And the models love this because it makes it easier to meet climate goals while also providing a fuel. So you can displace fossil fuels and provide negative emissions. From a modeling perspective, that's really, really nice. There are some scenarios that show zero bioenergy combined with CCS. And these are scenarios that are explicitly designed with that in mind, because there were a number of modeling exercises trying to show if we could meet strict climate targets without BECS, and it was possible in some cases, but not the preferred method of the models, not the preferred solution. So then moving on a little bit onto the land side, here we see the land cover for energy crops for all of these scenarios. And what we see here is that there's a very huge distribution of results. So while generally we see a huge distribution of results on all the panels, here it's there's no clear average, so to speak. The distribution is quite uniform. So we start entering huge areas of uncertainty here. And this is also shown in the AFOLU CO2 emissions. But I think the next speaker is going to probably be talking a little bit more about this, so I'm not going to say much here. But ultimately, what we see in the role of bioenergy in 1.5 scenarios, and as is cited in the AR6, limiting or excluding bioenergy and or BECS increases mitigation costs and may limit the ability of a model to reach a low warming level. So broadly, all of the integrated assessment models agree that this helps us meet climate goals at the cheapest possible level. And in fact, without BECS, many models find it infeasible, especially to meet the 1.5 degree target. This carbon dioxide removal that BECS offers is very, very important in meeting strict climate goals. Now, what we do see in all of these figures is these huge ranges. So there's immediately, even by looking at these high level results without looking into the details of the results, there's a huge amount of uncertainty. So where does this, and that's what I want to talk about now a little bit, is the role of uncertainty in these projections and what it means concerning the insights we can derive about bioenergy and climate targets. So where does this uncertainty come from? There's multiple sources. One is scenario uncertainty. As I mentioned in the beginning, these models typically have certain inputs concerning economic growth, population, and demand for energy services. We don't really know how these will go, and we don't know what they're going to be like in 2050, and we definitely don't know what they're going to be like in 2100. So there's lots of assumptions that go in there, and this is where scenario analysis becomes really important. Furthermore, we also have uncertainty on how the protection of land and biodiversity may change into the future, which obviously affects bioenergy a lot. And then another huge source of uncertainty comes from model specificities. So different models have different methodologies on how they solve to meet certain targets. Also, how they solve to determine the demand for energy and land use services for agricultural products and things like that. They may consider their completeness on the different types of land that they model, the different technologies, the different fuels and conversion methods. So that immediately would lead to different results. And then finally, there's parameterization, how they deal with the costs, efficiencies of technologies and how those develop into the future. So all of these uncertainties, basically, they add up to lead to massive compounded uncertainty. And now I have a couple of slides where I want to dive into a little bit and trying to understand what this uncertainty may look like and what does it mean concerning interpreting the results. So looking first on land availability, here I'm going to give an example from the image model because it's the model that I'm by far the best acquainted with. And just to quickly explain to you how we determine the land availability and thus the biomass availability in different scenarios. So we typically have this so-called food first principle. We make sure first that we meet all food requirements throughout the projection period, because in principle, we want to make sure that bioenergy supply does not interfere with access to food. So we make sure food access is achieved. And then we put some other constraints on areas of high biodiversity or environmental value. We avoid forests, we avoid areas with very high carbon stocks. And we generally put a lot of different constraints. And then in principle, we find land which in principle is available to produce biomass for energy purposes that does not have massive environmental implications. And here we see, as an example, one of those maps for an SSP2 baseline, where you see that there is quite a bit of land available. I'm showing this in the form of a grid cell fraction, typically between 20 and 60% of a grid cell, wherever a grid cell is available. And we see that it's concentrated in some areas. But obviously, different models could have very different methodologies on how they do this. Economic models tend to have direct competition between biomass production and food production, which would lead to a very, very different result on the potential. So immediately, this is one huge source of variability across the models, which then trickles down into their bioenergy demand, mitigation potential, use of BECCS, and so on and so forth. However, besides this methodological uncertainty, there's also the scenario uncertainty. How would this map here change if agricultural production and productivity was different than in an SSP2 scenario? What if we were to have stricter results on the protection of natural land, such as the recently Montreal Kunming Protocol, which isn't accounted for in this map? So this is where we explore that uncertainty doing scenario analysis. And just to quickly drive you some of those results and what it may mean concerning our scenarios, here we see for 3 scenarios combined plots of energy production, that is that solid black line with the axis on the left, and land use change emissions, that's the dashed line with the axis on the right. And I'm showing it for SSP 1, 2, and 3 scenarios. If you're not familiar with those scenarios, I've also given my own little subtitles. SSP 1 is generally a world where everything works well. SSP 2 is a business as usual, which typically isn't that great. And SSP 3 is a bad scenario. So just to make my point, I'm just going to focus on the good and the ugly. What you can see in the good scenario is we typically have a massive increase in bioenergy production, increasing to over 100 exajoules by the end of the century. But we also see that dashed line falling precipitously to even a negative land use emissions, even within the next couple of decades. So we have a situation where we have large increase in bioenergy production, but also a huge decrease in land use change emissions. If we look at the ugly scenario, you kind of see the opposite thing. You see less bioenergy being produced, still much more than today, but less than the good scenario, and you see land use emissions being consistently high. So in the good scenario, you have your cake and you eat it, bioenergy and land-based mitigation. And in the bad scenario, you're just shooting yourself in the foot. You're producing biomass at an expense of land use change emissions. So this is where it becomes important also when thinking about the role of bioenergy in mitigation scenarios of how you do it and what are the ancillary policies you've put in place in protecting land use, in increasing agricultural yields, and things like that. You could have a good bioenergy story, you could have a bad bioenergy story, and that's what we see through this scenario analysis. Now, moving into another area of uncertainty, it's looking how the model projections on different bioenergy technology uses are. So here we're diving into a little bit more depth of how they use the bioenergy. And these are the results of a model comparison project that we did a couple of years ago, specifically on bioenergy, where for a number of models, we looked at how they used bioenergy to meet 2-degree scenarios. And this shows how they use it disaggregated across different technologies. The different colors are different technologies. The first thing I want you to focus on is the difference in the volume used. So some models, for instance, the grape model in the middle, uses up to 200 exajoules by the end of the century, while the Imiclim and image models are way, way lower, more closer to 50 exajoules. And the second thing I want you to focus on is the technology use, so the different colors. We see models that focus on bioenergy with electricity. We see models that focus with bioenergy with liquids. We see models that are a little bit of both electricity and liquids. And then we see models that have a different thing. They might even produce hydrogen. So there's a huge variation in how the models use the bioenergy. So while in some cases they may agree on the volume, how they use it is very different. And this comparison exercise also allowed us generally to get a better understanding of the areas where the models agree and areas where they disagree. So for instance, the models agree, first of all, that bioenergy is used a lot and it's used actively. We also saw that early on looking at the IPCC database results. They also focus and they agree on the importance of lignocellulosic feedstocks. While they do show some use of particularly sugarcane in tropical regions, the big increase comes from woody and grassy crops, so-called second-generation feedstocks. They agree on the importance of residues because this is seen as a cheap resource with very low land use change and low emissions. They agree very much on the use of BECS, as we saw earlier, and they agree typically on international trade. So a huge chunk of the bioenergy being used in these scenarios is consumed in different regions from where it's produced. Now, where do they disagree? As shown in the previous slide, they disagree on how the bioenergy is used. They disagree on the supply regions and thus the trade. So while they agree on huge amounts of trade, what the trade routes look like, they do not agree. They disagree a lot on the supply characteristics. So how much does the biomass cost and how productive are the bioenergy crops? They disagree on the total volume of biomass. And this obviously relates to the yields, the total bioenergy demand, where it's used and things like that. They disagree on timing. If biomass is used in the short term in order to help reduce emissions, or if it's used in the long term in order to provide CDR to overcome residual CO2 emissions in the long term. And they also disagree on how different regions use it, so the regional bioenergy strategies. So huge areas of disagreement that do not allow us to give very clear advice on the role of bioenergy in mitigation scenarios. Now, one final point I want to bring on is kind of the non-bioenergy use of biomass in mitigation scenarios and the role there. So we recently published a paper where we also looked into the potential contribution of biomass in, for instance, providing materials, specifically plastics. And what we see here is in this Sankey diagram, you see basically the carbon flows in the plastics industry in 2050, according to an SSP2 baseline. So first, on the left, we see the feedstocks that provide the carbon to be used in plastics. Then it goes into a plastic stock, and then finally end of life strategies. These can be either be litter and burned, they can go to waste and energy, they can be landfilled, or they can be recycled through different recycling routes. And what we see in the baseline is that waste to energy is generally very attractive because you get a benefit by providing heat and electricity. What if we were to put a carbon price in order to meet that is consistent with meeting a 2-degree target? Here we saw the model actually really liked sending plastics into landfills, because in principle, that's a form of permanent carbon sequestration. Of course, the model doesn't know that landfills have a whole set of other environmental problems that we really, really want to avoid. But purely from a carbon perspective, and when you put a carbon price, the model really liked sending this carbon to landfills. And then our final intervention scenario is what we call the circular bioeconomy, where we try to promote the use of biomass and we try to promote the use of recycling. And what you saw here is that the role of biomass increased a little bit. I mean, not a huge amount, because obviously biomass was very attractive in other energy uses as well. But we do see that from the plastics produced and the plastic stock, the chunk from biomass increases, and we see this huge amount of circulation of carbon within the system. And in principle, this is a form of carbon capture and usage, or carbon capture and sequestration, as long as in the long term, this carbon isn't emitted by waste to energy or open burning. So we do see that this may play an important role, especially if you expand it to other materials, such as, for instance, construction and things like that. So all of a sudden, you see biomass playing an important role rather than bioenergy and biofuels. So jumping into some conclusions. Yes, biomass plays an important and active role in mitigation scenarios. This is clear, there's broad agreement on that, up to 400 exajoules per year by 2100, but most scenarios really show 100 to 250 exajoules. So that is, according to our today's energy use, that's somewhere between, I don't know, a fifth and a third of our current energy use. In the long-term projections, it's more than 10 to 20%, but it's still a huge chunk of our energy use. In 1.5 scenarios, we see that as we basically try to increase the climate target, biomass, it's more of it and faster. It plays this active role. And it is predominantly supplied by lignocellulosic crops and residues. So different than the current biomass supply, biofuel supply that we see in the current system, dominated a lot by first generation crops. So this leads to the second point, which is that advanced technologies are preferred. And I didn't show the results here, but we did a couple of sensitivities. We see that the scenarios are not sensitive to techno-economic parameterization. So when we ran scenarios where we increased the price and of advanced technologies, the model still liked them. So even if there's huge uncertainty in the techno-economic parameterization, that actually didn't affect the outcomes. Bioenergy and advanced bioenergy was attractive nonetheless. And the no BECS scenarios that I showed you in the beginning, there were some scenarios with 0 BECS that actually met climate targets. They depend on they either depend on other CO2 removal strategies, so like extreme levels of afforestation or direct air capture, or extreme changes in lifestyle and efficiency. So the so-called low energy demand scenarios, which show that our energy demand is going to decrease even according to today globally. So it's up to you to decide which of these scenarios is more extreme or unrealistic, but those are kind of the trade-offs, either BECS or scenarios that have other extreme measures. Mitigation strategies have profound implications for land management. So IAM strategies are implicitly or explicitly account for very strong land governance. Typically in these 1.5 and 2 degree scenarios, we do not allow deforestation. We make sure that there's a lot of land zoning, protection for biodiversity, and we also assume that agricultural yields increase a lot. So these are really, really important to make these scenarios realistic, and that absolutely should be stressed. And yeah, land-based mitigation measures are absolutely critical in the mitigation scenarios. So this is zoning and all of that. And then there are just some of the uncertainty, sensitivities, and areas of a concern. Again, stress some, there's many more beyond this list. IAMs adopt a plethora of methods, each with its own energy and land use strategy. So I tried to illustrate a little bit about what how these methods may vary and the different outcomes that they may produce. IAMs typically do not take into account deployment logistics, which may be very important. So seasonality, infrastructure, and international trade. And we recently did an exercise where we linked with a more bottom-up model to see specifically for Europe what the infrastructure implications would be for what we project for Europe. And though what we saw is that it was actually quite a bit worrying. So the infrastructure needed just for the European biomass strategies was way more than the infrastructure that currently exists for fossil fuels. That's what we noticed. So that may affect that may raise some feasibility concerns that typically IAMs are not very good at representing, and more work has to be done there. And then obviously there's the broader sustainability implications, be it biodiversity, water, and things like that. And increasingly, a lot of exercises are being done to understand those a bit better. So that's all I really wanted to discuss right now, but I'm open to questions and discussion. Thank you very much.